Inside JWST's giant mirror in early 2024, astronomers locked onto Betelgeuse, expecting the quiet aftermath of a dying star's violent hiccup. Instead, the infrared revealed a second heartbeat buried inside that orange light, something orbiting so close it may already have been swallowed. And the countdown we trusted was wrong. Step outside tonight and find Orion. That orange shoulder in the upper left corner of the constellation is Betelgeuse, a red supergiant so bloated that if you dropped it into our solar system, its outer edge would swallow Jupiter. It is roughly 650 light-years away, which means the photons hitting your eyes right now left the star before the printing press existed. You are not looking at Betelgeuse. You are looking at its ghost. For most of the last century, astronomers thought they understood this ghost. Betelgeuse is a massive aging star, burning through the final chapters of its life. Hydrogen ran out in its core long ago. Helium followed. Now heavier elements are stacking up like ash in a fireplace running out of fuel. Every stellar evolution code agreed on the ending. One day, without warning, the core would collapse. Gravity would win in a fraction of a second, and the star would explode as a Type II supernova, bright enough to cast shadows on Earth at noon. The question was never if, the question was when. And the consensus answer, drawn from decades of stellar evolution codes, was reassuring in its vagueness. Sometime in the next 100,000 years, maybe tomorrow, probably not for a very long time. Then in October 2019, Betelgeuse started to dim. Not slightly, not gracefully. It dropped to less than 40% of its normal brightness by February 2020, becoming visibly darker to the naked eye. Amateur astronomers noticed. Professional astronomers panicked in polite, careful language. Social media did not bother being polite at all. Everyone asked the same question. Is it going now? The Very Large Telescope in Chile turned toward the star. Miguel Montargis and his team used the sphere instrument to resolve Betelgeuse's disk, something almost impossible for any other star. What they found was strange, but not fatal. A cool patch had appeared on the southern hemisphere. Above it, a plume of expelled material had condensed into dust that was blocking the light from reaching us. The Great Dimming, published in Nature in 2021, was reinterpreted as a violent burp rather than a death rattle. A giant convection cell had lifted material off the surface, and dust had done the rest. That should have been the end of the story. It was not, because tucked inside decades of brightness data was a rhythm that no one could quite explain. Betelgeuse pulses. Everyone knew that. Red supergiants breathe in and out on cycles of around 400 days, driven by their own internal physics. But hidden underneath that main pulse was a second, longer beat. A rhythm of about 2,170 days, almost 6 years long, that stayed too regular to be random, too clean to be a coincidence, and too stubborn to fit the standard model of a lone dying star. At first, everyone assumed the long period was just a strange side effect of the star's chaotic surface. Massive convection cells, the size of continents boiling up from beneath, rising, sinking, dragging the brightness up and down. Simulations by Bernd Freytag and others tried to reproduce that 6-year signal using nothing but convection. They failed. Convection is turbulent. It is messy. It does not tick like a metronome. Whatever was creating that second beat was not chaos. It was a clock. And in astronomy, a clock inside a star usually means one thing. Something else is there. By 2023, a team led by Goldberg at the Flatiron Institute, working with Lars Bildsten and Morgan McLeod, asked a question that had been sitting in the data for years. What if Betelgeuse was not alone? What if a smaller companion star, buried in the outer atmosphere of the supergiant, was orbiting once every 6 years, clearing dust and modulating the light we see? They called this hypothetical partner Betelbuddy, and suddenly the numbers began to fit in a way convection never could. But a companion that close to a red supergiant is a companion in trouble. Betelgeuse's atmosphere extends far beyond its visible surface, thin as vacuum in places, but still dense enough to slow anything moving through it. A small stellar body orbiting inside that gas would not survive forever. It would spiral inward, dragged by friction, feeding matter and momentum into the giant, which raised a colder question. If Betelbuddy is real, is it still there? Or did we spend the last few years watching a companion that was already dying inside the light of a bigger star that is also dying? And if the second beat we were listening to belonged to something that has now been consumed, then whatever the great dimming was, it was not the whole story. Astronomers went looking for Betelbuddy directly. In late July 2024, teams pointed the Hubble Space Telescope and the Chandra X-ray Observatory at the star, timing the observation for the exact orbital moment when a companion should be furthest from the giant's glare. If Betelbuddy existed, this was the best chance in years to catch it. Everything ready, everything aimed. The result came back in early 2025. Nothing. No clear ultraviolet excess where the companion should have been. No X-ray signature. No unambiguous point of light. Just Betelgeuse, alone in the frame, exactly as it has always appeared to human eyes. You might think that ends the theory. A companion nobody can see is a companion that does not exist. But in science, absence of evidence is rarely the same as evidence of absence, and the Goldberg team had already considered this possibility. A small, hot companion inside the outer envelope of a red supergiant would be dimmed by the surrounding gas. Its ultraviolet light would be absorbed and reprocessed. Its X-rays could be blocked entirely. Or worse, the companion might no longer be there at all. It might have finished its slow, silent fall into the giant. It might have been eaten while we were arguing about dust. Now think back to that 2019 dimming. The dust plume was real. The convection cell was real. But something had to lift that material off the surface with enough force to create the largest known brightness change in Betelgeuse's recorded history. A companion tearing through the outer atmosphere is exactly the kind of trigger that could do it. Not the sole cause, not the whole answer, but a stir, a push, a partner disturbing the surface of a giant that would eventually have burped anyway. This is where James Webb enters the story. In infrared, dust becomes transparent in ways that visible light cannot manage, and JWST's MIRI instrument can see structures around Betelgeuse that no ground-based telescope has ever resolved. Astronomers used it to map the star's extended atmosphere, hunting for the fingerprints of an engulfment, asymmetric shells, warmer regions where a companion's kinetic energy would have deposited heat, chemical signatures that only appear when a smaller star is torn apart inside a larger one. The results are still being analyzed and debated, but the picture they suggest is not the picture we had 5 years ago. The old picture was a lone dying star, pulsing quietly in its own light. The new picture is a giant that has been sharing its atmosphere with another body, possibly consuming it, and that internal violence leaves traces. Mass gets churned. Fresh material gets dragged inward, changing the balance of temperature and pressure near the core. And here's the part that unsettles everyone. Even a small change in that balance can shift how quickly a star finishes its life. In 2023, a team led by Hideyuki Sayo published a paper suggesting something that most astronomers still find hard to accept. Their pulsation models, matched against decades of Betelgeuse's brightness data, were consistent with a star that has already burned through helium and moved into carbon burning. Carbon burning is not a distant stage. Once a massive star begins fusing carbon in its core, the clock is no longer measured in 100,000 years. It is measured in centuries, maybe less. Most experts remain skeptical of SIO's timeline. Pulsation modeling of red supergiants is famously difficult, and there are several ways to fit that data that do not require carbon burning at all, but nobody has been able to completely rule the possibility out. And when you combine SIO's minority result with the growing evidence that Betelgeuse has been quietly hosting and possibly digesting a companion, a colder question forms in the back of your mind. What if the internal age of the star and the external age we have been assigning to it are no longer the same number? Now hold that thought and think about your own sun. 5 billion years from now, our sun will swell into a red giant of its own. When it does, its outer edge will reach past Earth's current orbit. Whatever remains of this planet by then will be engulfed the same way Betelbuddy may already have been engulfed. Watching what is happening around Betelgeuse is not just watching another star, it is watching the future of every rocky world orbiting a star that will eventually die. And that is where the reversal lands. For 100 years, we have been listening to Betelgeuse as if it were a solo performance. One massive voice, singing its long, slow song toward the end. What we are starting to realize is that we have been listening to a duet, and one of the singers has gone quiet. The star we thought we were reading was actually two objects entangled inside a single point of orange light, and the final warning may not be coming. It may already have happened, and we simply do not know how to hear it yet. So what do we actually know? Strip away the headlines. Strip away the fear. Strip away the certainty that neither the data nor the physics can support. What survives is a picture of Betelgeuse that is stranger than the one we had before JWST, but not the picture the internet has been selling. Here is what has been directly observed. The great dimming of 2019 and 2020 happened, and it was caused by a dust plume above a cool patch on the star's surface. That is not a hypothesis. That is imaged. The 2,170-day pulsation exists in the brightness record. That is measured. JWST's infrared observations show structures in the extended atmosphere that were not visible from the ground. That is data. Here is what has been calculated from that data. The long pulsation, if orbital, corresponds to a companion of roughly 1 solar mass moving through the outer envelope. The dust production rate has changed subtly over the last decade. Betelgeuse is still around 650 light-years away. Its mass sits somewhere between 15 and 19 suns. Here is what is inferred. The companion, if it existed, has likely been consumed or is currently hidden inside the giant's outer layers. The 2019 dimming was probably triggered or amplified by this interaction rather than being an isolated event. Betelgeuse is more disturbed, more chemically mixed, and more difficult to model than the classical picture of a lone red supergiant allowed. And here is what remains speculative, that the internal clock has been quietly running faster than the surface reveals, that carbon burning may already be underway, that the supernova is coming in centuries rather than millennia. None of these ideas are impossible. None of them are proven. They live in a range where honest scientists disagree, and disagreement is not the same as knowledge. So when the title says JWST captured Betelgeuse's final warning, and it is sooner than we thought, here is the honest translation. The warning is not a flare. It is not a countdown to a specific year. It is the realization that the star we thought we understood is more complicated, more disturbed, and more capable of surprising us than the models predicted. The consensus timeline is still measured in tens of thousands of years, with a strong central estimate closer to 100,000. That has not fundamentally changed. But the tail end of the probability curve, the small dangerous edge where the star could go within a human lifetime or within a few generations, has grown a little heavier. Not enough to panic, enough to matter, enough to make an astronomer pause before saying nothing interesting will happen in our lifetimes. And if that edge is real, if some morning or evening in the coming decades, we look up and Orion has a stranger blazing where its shoulder used to be, this is what we would witness. A single point of light, bright enough to see in daylight for weeks. A slow fade over months. The first naked-eye supernova since Johannes Kepler stared into the sky in 1604. No danger to Earth, no radiation harm, just a moment when the sky itself rearranges, and every human being alive stands under a shared strangeness that no telescope on the ground can ever fully explain. Now go back to that orange shoulder in Orion. Look at it again in your mind. It is no longer a lone dying star. It is a crime scene with a missing accomplice. The dust you now know is real. The pulsation you now know is not one beat, but two, and one of them has fallen silent. The light entering your eyes tonight left the star 650 years ago. Everything it is telling us is already ancient news, which means the real question is not whether Betelgeuse will explode. It will. The real question is whether the star we are watching right now, in this instant, has already begun the sequence and is simply waiting for the news of its own death to finish crossing the distance to us. Somewhere between here and the constellation of the Hunter, that news may already be traveling. Photons carrying the final image. Neutrinos moving just a little faster, arriving hours before the light. There is one final unresolved question that keeps the researchers who study this star awake at night. If Betelbuddy was consumed, when did it happen? Because a companion falling into a giant does not just disappear. It sends a shock wave through the outer envelope, and that shock wave has to travel down toward the core. If it reached deep enough, it could have mixed fresh fuel into places the models never accounted for. And if it did, then somewhere beneath that orange light, a core that we have been treating as slow and predictable may have already been shoved into a stage we cannot see from the outside. We will not know until the neutrinos arrive.